Okay, so at this point, we have a whole lot of different tests to determine convergence or divergence of a series. We have the nth term test for divergence. We have the rules for telescoping in geometric series. We have the integral test, the limit comparison test, the alternating series test, and the ratio test. There's one more test that your book doesn't include that I might make a video for, but it's not required. It's kind of an extra one, but I might add that later. But for right now, we actually want to look at something slightly different. And I've said this before in class when we were seated and on these videos, that sometimes what we do seems a little bit bizarre, like why are we randomly doing this new thing? And that's also true today. We're going to take another left turn and do something slightly different. And once we kind of get a little bit more into it, probably not with this lecture, but with like what we'll do on Thursday, it will make more sense, the goal here. But we're going to look at another type of series and mess around with it a little bit and look at our convergence and divergence and things like that. And it's what's called a power series. You may have heard of power series in 171 when you were talking about polynomials and how you graph polynomials with their end behavior and things like that. The end behavior is actually based off of a power series. So you may have seen it before. If not, the way we're going to write our power series is the series n equals 0 to infinity of c sub n x to the n. So essentially something like 1, we know that's a sum, so 1 plus x plus 2x squared plus 5x cubed plus whatever, and on and on and on. Essentially a polynomial, which is how you would have viewed it in 171, but we're going to call them power series. There is a little bit, just to make sure we're clear here on what's going on, there is a little bit that's important. One thing, when you have a power series, you actually say the power series centered at a point. So this is kind of one form of the power series, but it's actually a special case. The more general form is the series n equals 0 to infinity c sub n x minus a to the n. Here, a is just equal to 0. And bear with me for 1 second. My cat has gotten onto the cat tower, and he's going to make the video move, so there we go. Goodbye, cat. Okay, good. So, in this case, this is just a special case where the power series is centered at 0, so that's x minus 0. But in general, we can center our power series anywhere we want. And again, I don't want to go into this at an incredible length because we will cover it later on. But the idea is, the ultimate goal of this class is to be able to integrate everything. We've said that repeatedly. And now the other cat's coming for the cat tower. Okay, good. The ultimate goal is to be able to integrate everything. And we had all our tricks for integration, and we integrated as much as we could, but clearly there are functions that we cannot integrate. Now we have spent some time looking at series and determining when series converge and when they diverge. Now what we're going to do and kind of flesh out today and on Thursday is, well, we talked about the trapezoidal rule and Simpson's rule where we could approximate the area under a curve using those different tricks. Now maybe I can use a similar idea. Maybe I can approximate the value of a function around a given point. Meaning, maybe I have some function, f of x equals e to the x. And again, nowadays we can get really accurate values. Go away, cats. They seem to be enjoying the cat tower today. Go away, cat. Okay. Nowadays, you can throw it into your calculator, throw it into Maple, and you get a value. But assume you lived a few hundred years ago and you don't have a calculator or anything, how do you find the value of e cubed or e to the 2.5? You can't do it like into a calculator long form, but maybe if you could find a nice function We just said these power series, when you expand them, look like polynomials, which are nice functions actually. If I can find a way to approximate the value of this function with a polynomial, and I can evaluate the polynomial, then I can essentially approximate the value here. And that's ultimately our goal, to see if we can find different series, and we will learn different tricks. Right now we're just learning the basics of power series, which are one trick, where essentially we'll say, given a function, either the x, sine of x, log of x, can I find a power series that will approximate the value of this function? And then, since I can't evaluate this function, because I don't have a calculator or anything, because I lived a few hundred years ago, then I'll approximate it with the polynomial, the power series that I've created. And we've repeatedly, on all of those things like Simpson's rule and the midpoint rule and trapezoidal rule, talked about error. Then maybe we'll say, as long as I can approximate it within a certain amount of error, then I'll be good to go. And that's kind of the end game here. But in order to get there, we need to have a good understanding of these power series and what's going on, which is what we want to spend the rest of this time doing. And the one thing to keep in mind, the most important probably for now, these are series, they're power series, but they're still series, which means all of our rules for convergence and divergence still apply. So, for the sake of argument, since we've spent so much time talking about convergence and divergence, suppose I have this one. The series 0 to infinity, n x to the n, 5 over 5 to the n. That's a series. I want to know if it converges or diverges. Well, we can run all the different tests we want, but the test we're actually going to use for these power series, and it will work for all power series that we're going to look at for now, just use the ratio test. So, throw this into the ratio test, and let's see. I don't need to worry about absolute value because everything is positive. I'll write it, but you don't need to worry about it. And it's, let's see, a to the n plus 1 over a to the n. So for us, that is n plus 1 times x to the n plus 1 over 5 to the n plus 1 all over n x to the n over 5 to the n. If I simplify all of that out, let's see. I have x to the n plus 1 over x to the n, so that leaves me with an x on top. I have 5 to the n plus 1, which is going to go on the bottom. 5 to the n is going to come to the top, and I'll have a 1 5 left over on the bottom. And then I have n plus 1 over n left over. Now, let's see. I need to figure out what the limit of that is as n approaches infinity. And one thing to keep in mind, if I take the limit as n approaches infinity, the x and the 5 are constants. They're not affected by the limit, which is the limit for n, not x. So I can pull that out of the limit. And I end up getting x over, the absolute value of x over 5 times the limit as n approaches infinity of n plus 1 over n. And now this limit is easy enough to see. That's just linear over linear. So it's going to be quotient of leading coefficients, which is 1. So this whole thing is going to approach 1. So the limit here is actually absolute value of x over 5 times 1, which is x over 5. And now as far as our convergence and divergence goes, the ratio test says what? If the limit is between -1 and 1, or the absolute value is less than 1, it converges. At 1, you get inconclusive, and if it's bigger than 1, it diverges. But here my limit is actually variable based off of x, which is kind of the other important difference between these power series and the other power series we've looked at. These are the first series that have x's in them, variables, which means they're actually functions. If I wanted to up here, I could have called this f of x and defined the series as a function of x, that variable right there. But what it means is Well, if I want this to converge, it's going to converge where the limit is less than 1, but the limit is actually variable based off of x. So now I have to solve the equation. Or in this case, not an equation, it's an inequality. You all remember how to solve absolute value inequalities? This becomes -1 is less than x is less than 1. X over 5, I'm sorry, is less than 1. Then we multiply the 5. We get -5 is less than x is less than 5. And now what that means is, if x is between -5 and 5, don't cat. If x is between -5 and 5, then this limit will be less than 1, which will then make it converge by the ratio test. If x is outside of those bounds, this limit will be bigger than 1, which means by the ratio test it will diverge. There's a little trick for these actual endpoints at -5 and 5. Don't worry about that today, we'll cover that later. But for right now, it means within this range, that series will converge, which means it converges for some x's, but not all of them. And if you look over here, that does make sense. This, for the most part, is almost geometric. It's x to the 5, x over 5 to the n.